Okay, right. I think I have this set up so it is streaming to YouTube, which will then hopefully record it as well. I'll just make sure that that's happening and then I will get started. Okay, just very nearly there. Um, okay, so apologies for that. I think this is now all recording, so I should be able to get started. So as we said before the lunch break, this session is going to be a bit different from the previous three sessions in that this really is just designed to give you an overview of various things which you really should know about and which you should go off and learn more about in your own time about about good principles and practices for both building your code and turning that into from going from scripts to going to actual software, and in things which you can do to make collaboration with other scientists and other programmers easier, as well as then going on to distribute your code. And even if you're not doing a lot of collaboration with other people over your code, in a sense, you are collaborating with your future self. So lots of the practices which I'll cover should also be useful for you when you come back to use your code at some point in the future, or when you need to run things in that one hectic week as you are doing the final edits to your thesis before handing in. That Not that anybody would be that disorganized, and certainly I did not have a hectic week immediately before handing in a thesis at all at any point. Of course, most of us as scientists, we find ourselves writing code to get answers to some of the deeper questions about different aspects of the universe, rather than for the fun of just writing code. Now, for some of you, it may also be for the fun of writing code to some extent, and there is no judgment if that is the case. But frequently, we don't really think about code as an important product of our research, um, but rather as just a means to an end. And it's a very tempting trap to fall into, that to to treat your code as just a means to an end rather than an important part of what goes into your research itself. And it can be quite a dangerous place to find yourself. I, Aside from anything else, you spend a lot of time writing your code. You have good reason to be proud of it. Um, your science should be reproducible, um, and you should make reproducing your results and your science easy if you can, for the sake of other scientists who might want to come along and look at your code. And of course, research is expensive, and most of us are funded either ultimately by taxpayers or by some institution, which would probably like us to share code with other people so that we don't keep paying to reinvent the wheel. Um, of course, writing good code is sometimes far harder than writing bad code. But from my experience anyway, any increase that you get in speed from dashing off code is almost always made up for later on, whenever you've got to go back through and pick through your bad code to work out what was going on in the first place. And maintaining bad code is much more time consuming than maintaining good code. So in these slides and in this talk, this part of the session, I'm going to focus on examples which come from Python and from the development ecosystem which is built around Python. There's a simple reason for this, which is that we had to choose some language to give examples in, and Python is a popular language and a language of increasing and growing popularity particularly within physics. It's certainly not the only language which any of these principles are applicable to, and really the vast majority of programming languages should support all of the principles and the practices which I'll talk about. This is also the last time I have a picture of a snake in the slides, just in case that's a problem. So I'll split this afternoon's session into 3 parts. First, I'll talk a bit about modularizing your code, that is, breaking it up to make it more manageable. And in certain respects, this is one of the more Python-specific parts, although again, principles from this will transfer across to lots of other languages. Then we'll take a brief break, so I'm hoping each session will last a little under an hour, modular recording problems. In the second session, I'll talk a bit about how you can improve the quality of your code and simple and sometimes not so simple things which you can do to do that. And that includes how to test your code and how to document it to make sure that your code remains viable as it develops. And then in the final section, I'll talk about packaging and distributing your code and the things which you need to do to prepare your code for publication and for inclusion with the supplementary data, perhaps, of a published paper, for example. So I'm just going to launch straight into the first section, which is on modularization. Well, what is modularization? Well, modularization is something which you may have touched on already if you've taken a programming course in something like Python, but frequently this is something which is kind of skimmed over. So if you've got a big script which is full of lots of different functions and so on, you'll want a way of splitting things up so that it's easier to maintain the code. Now, the first thing which I want to talk about really is specific to certain types of programming languages and not all programming languages, and that is object-oriented programming and classes. I'm going to go through this quite quickly. This applies to languages like Python, like C++, and some other languages do have some notion of object-oriented, and Java is another major example of a object-oriented language. Some languages which a lot of you might use, like IDL and MATLAB, may have some concept of objects and classes, but they're very far from the standard way of using those things in those languages. So while this may not immediately seem applicable if you're mostly, for example, a MATLAB programmer, hopefully some of the things which come out of this will still be useful. And it's only a few slides, fortunately, anyway. So in Python and object-oriented languages, classes are a development of the concepts of principles which separate functions and variables, so data and procedures, apart from each other. And object-oriented programming uses something called an object, which combines those data with the procedures which are specifically designed to operate on them. And that gives you the advantage of maintaining both logical and organizational connection between these two components. And I have some examples in later slides which will help to make this relationship a bit more concrete. And in Python and many other languages, these objects are constructed using a blueprint which is called a class. So the class just explains to the programming language how the data and the procedures should relate to each other. So it is easy to get confused between what a class and what an object is, and I know this full well because I had a student who got very tied up in a lab earlier this week about this. So the important takeaway is that a class is the thing which is used to create an object, and an object is an instance of that class, so it is the thing which has been created with it. And again, I have some examples which will hopefully make this a bit clearer. And kind of an aside here that Python and C++ are examples of languages which use classes to build these objects. If you ever find yourself using a language like JavaScript, they do things slightly. Some languages do things slightly differently using something called a prototype, which is a principle in which objects are built up from less complicated objects, and you keep iterating and adding new bits onto them. In many respects, the two approaches are actually quite similar. But I'm not going to talk any more about JavaScript today, which may be a relief to some of you anyway. So let's have a quick look at an example of a situation where we might use object-oriented programming. So say you've just decided that you want to start automating all of the kitchen appliances in your house so that you can connect them to the internet and you can start to operate them via the internet, because that is a modish thing to do these days. And you've got your coffee machine, and you need, in order to connect to your coffee machine over the internet, you need to run some code which tells Python how to actually communicate with the coffee machine and sets up a connection between your computer running the code and the coffee machine. And then you want to write up some functions which will do something with the coffee machine. So like heating coffee, or heating water to make coffee. You kind of follow what's going on here. So in conventional Python, your script to do this might have this sort of outline that you define a variable which is the name of the coffee machine. Then you have a function which takes the name of that coffee machine, goes and forms the connection, and then you've got a second function that takes the thing which comes out of that setup function and actually operates on it to perform the heating of the coffee. So you end up with several steps which you need to remember to run each time. So you need to remember that you need to set up the coffee machine, and then you need to run a function to heat the coffee. So object-oriented techniques allow you to simplify what this looks like slightly, or at least to kind of pull things together in a slightly more logical manner. So the ideal thing which object-oriented programming will let us do is cut this down to just 2 lines. One where we make the machine as something called as this coffee machine thing. So this would be a class which takes the name of the coffee machine as its argument. And then we can run on machine.heat. So this is the procedure which is running on the machine object which is created by this class. So let's have a quick look at what way you would go about actually converting the code into this. So the class, this blueprint for interaction with the coffee machine, takes a kind of specific form. So we give it a name, a bit like you do with a function in Python. But then we have a special function, a special procedure, which runs whenever it's created, and we have and then we have the procedure, the heat procedure, which we can run on it. So I'm just going to add labels to this and talk through what's going on here. So we have various things which are happening here. So we create the class with this class coffee machine. By convention, classes are named with capital letters, and in Python with by capitalizing each subsequent word. We can add variables to the class which every instance of that class should know about. So for example, if I have some dictated ideal temperature for coffee, which is 86, then this can be included within the class. That's something which we call a class attribute. And I'm going to introduce a lot of kind of technical terms here, which from the point of view of actually writing the code don't really matter, but which it's kind of worth knowing what these things are if you're looking at documentation, for example. Then we've got this def init function. So we've got a function declared within the class, and functions which exist within the class are called methods. And this underscore underscore init underscore underscore function is a very special one which basically all classes require, and it's something called a constructor. So you never run this method, or you would not normally run this method manually, so you wouldn't call it specifically. But when we ran this machine equals coffee machine name equals brewmaster line, what happens is this Python runs this method, which takes the name, and it does and it sets some internal variable called name, and this is where we would include our setup code. So the code which we had in a separate function earlier to automatically do whatever connection you need can go in here so that it's automatically run whenever the object is created. We then, so this, you'll notice that there's this self thing which has appeared in the definition for this function, which didn't appear when we called it. So Python automatically passes the object itself to all of its methods when it runs, so that the code inside the method can operate on the object itself. And what's happening here is that we are taking name as an argument for the constructor, so for the construction of the object. And we are saving it to a variable inside the object called name. And we do that by saying self.name should equal name. So this self.name is a variable attached to the object called an attribute. And if we wanted to call that in our Python script, we could do that. So we have it the object called machine, and if we ran machine.name, that would have the value of name as passed through this way. So yeah, and so this self is a special variable, and you should always call it self by convention in Python. I've never seen anybody calling it anything else. You technically can, but you shouldn't. All right, this is kind of a whistle-stop tour of what an object is, but it's kind of important for what's coming along later, and some of the principles which I'll talk about later. When we break off, I can take any questions which we have about this, but hopefully this is kind of useful and it will help to explain how some of the underlying aspects of Python work as we go through. But don't panic if this didn't all sink in right away. So as you start writing more and more code, it's very likely that you're going to find that you have some functions and maybe some of these classes which you keep reusing over and over again. And at some point, and hopefully at some point quite early on, you're going to realize that, for example, copying and pasting functions between different scripts is not desirable. And that you want to have a way of reusing blocks of code which live somewhere in multiple different scripts. And this is what modularization is designed to help you achieve. So the idea is to start taking these reusable bits of code and gathering them together into modules. It also has the advantage that your scripts are actually physically shorter and easier to understand if you don't have screeds of function definitions, for example, at the start of every single script. Python calls these collections modules. Other languages call them libraries. It's more or less the same thing. If you've done a C course, there's a decent chance that you are more aware of this sort of principle than you are if you've taken any of the Python courses, which I know. So if this all sounds familiar, that's good. And hopefully things will make lots of sense to you later on anyway. So in Python, if you are a Python user, you'll probably be familiar with the import keyword, which is all related to modularized code. So suppose that we've saved the coffee machine class somewhere, and we've saved it into a file called coffee.py. Then if we want to write a new script, which will actually do the running of the coffee machine, and we call it coffeetime.py, and it wants to do something with the coffee machine, we can access it by adding this import statement into our code. Now, this relies in the way things are currently set up that your coffee.py script and your coffeetime.py script are in the same directory. So you run import coffee, and then you can run the rest of the script more or less the same way as before, but this time we use machine equals coffee.coffeemachine. This coffee.coffeemachine thing is a is what we call a namespace. So Python separates everything which comes out of this module into a different namespace so that if you had uh, a an object, for example, from a class from a different module which had the same name, one wouldn't overwrite the other one in a confusing way. But otherwise, the script looks broadly the same, and you can see we managed to keep this down to 3 lines of code in our script, plus the module. And to get around this namespacing issue, to make things less confusing, if you want tidier, if you want, you can also use syntax like from coffee import coffee machine. And if you've used much Python, you've almost certainly seen things like this. For example, to import things like matplotlib, which is the major plotting library in Python. Now we can start to complicate things a bit in terms of modularization by splitting the code into multiple different files. So say I've gone insane and decided that I want to write code to connect to all of my kitchen appliances some weekend. And I want to make an entire module which I can access from any computer in my house which I can install on any computer in my house to access, different things in my kitchen. I might want to keep the code for each of those things in a separate file. You don't particularly want your coffee machine, your toaster, and your fridge all being described in the same file. So if we have multiple different things, we might separate things up so that we could run an import which looks something like from kitchen.coffee import coffee machine. Now, what do we need to do to make this work? So before we just had our coffee machine sitting in a single file called coffee. We've now made things a bit more complicated, so we now need to set up a specific directory structure. This directory structure is how Python organizes, how Python starts to organize modules into what we call packages, and we'll come back to that really towards the end of the session. But we have we now have and this is confusing, and I can only imagine I was hungry yesterday when I was writing this. I've called this breakfast in this image, and I meant to fix this. This should really say kitchen. So where you see breakfast, think kitchen, and I can only but we have so the name of the overall name of our module is the name that we give to the directory. So breakfast or kitchen, ideally. And then we would move coffee into this directory, and we'd have all of our other appliances like fridge, toaster, and so on in here. And we need to include one additional file which can be empty, so it can be blank except for the name, which is this __init__.py file. And this just tells Python when it's looking through the directory that that it should be able to import things from this directory. So it will ignore the directory if it doesn't have the init file in it. But if coffee time tries to run import, coffee from breakfast, in this case, it will look inside breakfast and then it will look for a file called coffee. And Python separates directories up with dots when it's doing this import process rather than /. So the init file can be blank, but you can also include code in the init file, in which case, in this case, if I had a class in the init file, for example, called appliance, I would be able to import it with import appliance from breakfast, as opposed to something like import coffee machine from breakfast.coffee, where it lives in the coffee file. All right, I have, in fact, gone through this quite fast, I realize. So I'm going to briefly to ask if there are any questions or comments. All right, I'll get a bit of a head start on the next section, and but still plan to break at about 10 to 3 for a little while, so that we're not all sitting at screens for too long in a block. So that's kind of a very brief overview of how modularization works, principally in Python. It's always a good idea to split your code up this way if you can. It just makes it a lot easier to maintain your code because you don't have multiple copies of the same thing spread around multiple different files, so that if you need to make a change to one function, you might have to go through and change, 10 scripts if that had been the approach which you take. And it's kind of following on from the same philosophy and methodology which Norman talked about a lot during the make session, where you really want to avoid repeating yourself as much as possible. So it is all about making ultimately your life easier, but making your life easier also makes your code better because it means that where bugs, for example, come into your code, they are easier to fix if you only need to fix them in one place, and uh, it makes making modifications, even for adding extra features, just generally easier. So in terms of finding bugs and trying to and problems in your code and trying to um, you, maintain the trying to make sure that your code maintains kind of quality over time. So even as you change it, um, it's a good idea to start testing your code early on and to think about strategies for testing your code and making sure that it continues to work as you go through the code development process. So yeah, over time, it's likely that your code will change. So you might be adding new features, or you might be deciding to do things to try and tidy it up. So that's, for example, refactoring your code. So if you are trying to move things around to improve the logical structure of your code, which will happen over time because as your code develops, you'll realize that, oh, well, really, I should have made various design decisions earlier on, which I did not make going into the process. And you want to make sure that as you make these edits to your code, that it continues to run and it continues to give you the results which you expected. Um, and so while you're writing your code, and for a lot of you, and certainly for me, and when I was starting out in research, the approach which I took to testing code was principally, you write a small block of code and then you run a script with it in and you check that it works. And then you decide, yep, that's working, that's fine. Or what's even easier to do now is that you write a function out in a cell of something like an IPython, a Jupyter notebook. You run it, it seems to work. If it doesn't work, you go try and fix it and you debug it that way. So that's okay while you have small amounts of code where you can reliably do that, um, and where it's not going to be time consuming to do that. But things are going to become more complicated if you are writing code for some much larger project, or where you're writing code which other people are going to work on, and where you need to ensure that this testing process still happens. But there are so while this can become a non-trivial task, there are strategies and tools which can help with this. So the first major piece of advice which I have, which is not really related to testing, but is related to maintaining well, it's not directly related to testing, but is related to maintaining the quality of your code and making things easier to work with, is having some potentially fairly vague um, style guide which you follow. So trying to write your code in such a way that it is kind of easy to follow. Now, Python puts a lot of stock into trying to make sure that code is readable. Python was principally designed to be a language which is easy to look at and understand what is going on. But again, this should apply to any language which you're working in, that you should try and make your code as readable as possible for your own sake, if nobody else's. Because when you come back to it later and you are trying to work out what is going on with this, you will thank yourself. Now, the most programming courses kind of start to introduce this. You'll be told don't call variables by single letter names, and put comments in your code. These are kind of things which hopefully you've been ideas which you've been introduced to before, but there are really more things which you can do to push beyond just that. For Python, there are numerous style guides. One of the most popular ones is the one which was developed by the Python Software Foundation, so the people who actually ultimately make Python, which establishes various conventions, and this is PEP 8. And to give you an idea of some of the suggestions which this makes about your code, if you have a look at the two examples on this slide, you'll see that they look quite different. You may be able to guess which one is written in better style than the other, but let's just have a look at what's going on here. So the one on the left, the first thing which stands out is that it has no comments at all. So it has no documentation. So Python has this this specific way of making comments at the beginning of something like a function or a class, to use to document it. So this is a thing called a doc string in Python, but other languages allow you to add longer comment structures than just a single line as well, and they'll have their own syntax for doing that. In Python, it is that the first line of the function or the class takes a string, and in Python, multi-line strings start with triple quotes. And then here I've just got some documentation which explains what which describes concisely what the function does and gives a brief description of its behavior. So this is useful because when I come 3 years down the line to look at my code again, try and work out what it does, it's useful both that it tells me what it's meant to output and how it behaves when I give it various keyword arguments. I'll come back after the break to talk about about strategies for making this documentation better. But for now, the fact that there is any documentation at all makes it better than the sample on the left. So then some other more nitpicky things about this, but still useful things to keep in mind, are that in this example, we've got a lot of excess space, which kind of makes it difficult to follow where the logic in the function is happening compared to where the function itself is declared. In Python, this kind of thing is a particular nuisance because Python white space is important in Python, and so losing track of white space can be a real nuisance. So white space in Python is used to separate blocks of code. But having vast amounts of excess white space, for example, can just make your code less readable. And then there are some other things going on here as well, like inconsistent spacing around things like equals signs. And the more nitpicky these things get, in a sense, the less important they become. And a word of warning about style guides is that I think it is possible to stick too rigidly to them. There are situations where a style guide will tell you you must do something this way, and then it frequently does not add to the readability of your code. But PEP 8 is generally pretty good for Python, and I would recommend at least looking at what it suggests and trying to follow most of the things which it suggests. It can be kind of difficult to stick to all of the rules and to spot places where you've maybe done something confusing just by eye. So there are tools to help with this. So in Python, Python, for example, has a tool called Pylint, which is designed to check for things like extra spacing around um, extra spacing, which maybe you don't need in functions. And this is kind of the very first step of testing of your code is running linting and something called static analysis. So this is a process where a script parses in your code, looks through it for situations where maybe your code breaks various guidelines, and it can identify places where these bad practices are taking place. Um, so, uh, so for example, when I ran the block of code which I described as good through Pylint, uh, it told me that my code had been rated at 10 out of 10. And one of the nice things about putting your code through Pylint is that if your code's good, it gives you some pleasant positive reinforcement. And there's nothing like a good geek likes more than being told that they get 10 out of 10 on a test. What happens though when I put the bad code through the linter? Well, first of all, I get 0 out of 10, which is kind of sad. But it more helpfully does give me some feedback, some useful feedback about what was going on. So some of these are more important than others. So trailing white space, you won't have been able to see in the example, but basically on some of the lines, there was white space at the end of a line, which didn't need to be there. I wouldn't worry so excessively about these things, these trailing white spaces. They're not as important as this line about the missing module docstring. So it will tell you if one of your functions or one of your classes, for example, does not have any documentation. Because occasionally it is possible when you are writing code to kind of leave that out and think, oh, I'll come back and do it later. But it's useful when you get reminded, no, you've done something unhelpful and you should go back and look at this. It told me, oh yeah, so my function here was called hello world with capital H and a capital W, but it's a function. So it objects to this because it says that this doesn't conform to snake case naming style. So for example, in Python, to make it easy at a glance to tell what is a class and what is a function or an object, classes always have capital letters in their names, as I said earlier, but functions and objects get named in snake case naming style. So it will tell you that you have named a thing in a way which might be confusing. And then again, it's complaining that something has missing documentation, and it has quite harshly told me that my code is rated at 0 out of 10. So I definitely feel the need to go fix that. But you'll get various different ratings, which can go all the way, rather upsettingly, with Pylint down to minus 10 out of 10. If you are a bad transgressor. So there's a more aggressive static analyzer in Python called Flake8 as well, which it's able to identify a lot of additional stylistic problems with your code. And my experience, Flake8 is really quite aggressive with, I know, possibly excessively aggressive with this process. And can identify lots of things which are just infuriating to be told about and do not help much. But it is capable of identifying some other problems with your code, like identifying places where indentation might be incorrect, or one particularly annoying thing which can happen with Python 3 code, which is where, so in Python you use indentation to separate blocks of code. You can use either tabs or spaces, but you can't use both in Python 3. You have to choose one or the other in each file. And Flake8, for example, is capable of spotting situations where you have used spaces inside a file which is using tabs, or one which is using tabs inside spaces. So it can be useful to be able to run Flake8 as well. So in the notes which I've linked on Moodle, there are more details about how you run Flake8. I'm not going to talk any more about it during this session. But this does bring me, I think, yeah, this brings me to the end of the section on code style and static analysis. So I'm going to suggest that we break for 10 minutes to get away from screens for a few minutes and come back at 3 o'clock. Are there any questions quickly before we do, though? Okay, I will take silence as happiness, and I'll see you back shortly. All right, let's get started again. So before the break, I was talking about using tools which look at your code and parse the code themselves to try and identify problems with it. And whilst these can identify some things which might manifest themselves into actual problems with running the code, they're not really a good way of identifying um, bugs and situations in which your code runs but doesn't run as you intended. So yeah, most bugs won't show up until you've actually executed the code. And there are a few approaches to testing your code for these kinds of bugs. And the simplest of these, and the one which I'm going to talk about first, is called unit testing, which is where we take individual units of code and we run them, and then we examine the behavior of that unit of code. So in Python and most other languages, a unit of code is likely to be either a function or a class method, but they can be other things potentially as well. But they're normally uh, the simplest block of code that you can have. So a unit test is not normally used to check the behavior of an entire script, for example. And these units are tested in isolation from each other, and there are a couple of reasons for that. The main one is that that allows you to identify problems quickly because you can see um, exactly which unit, which function, for example, is behaving differently to how you expect. But it's also normally faster to run functions in isolation rather than trying to push through all of the operations which happen in a script or the conventional way that you run your code. I will come back to talk about about strategies for dealing with how everything joins up after later on. So to kind of motivate and make concrete how you would go about writing unit tests, let's take an example. So suppose we're writing some code to identify whether or not a number is prime. So you see a very simple function here on the right. We want the function to return true if the input to the function is prime, and otherwise we want it to return false. Um, so right now the function on the right is a function which tests whether uh, a number is divided by some variable I is equal to 0, returns false. So if it is divisible by something, otherwise it returns true. You can see that this function is probably not going to work. But let's think about writing some tests which will check whether or not it works. Incidentally, the first thing which is wrong with this code, which is that I is never defined, is exactly the sort of thing which might be identified during static analysis, so during the previous step. But I've left mistakes in here to make it more obvious what's going on, I guess. So we might think about before we start writing tests, some edge cases and some different things which we want to check. So there are some specific things which we might want to check for a function which is designed to identify prime numbers. One is, will it identify 2 as being prime, since 2 is unusual in being an even prime number? Will it identify 1 as not being prime, since 1 is not prime because it is only divisible by 1, and 1 itself? What's the behavior when you test 0 or a negative number, for example, and what happens if the input to the function isn't an integer? And for the first two of these, there is an obvious answer to what you want. And the second two, to some extent, requires some design. And what do you actually want to happen when you ask for these things? Do you want it to return false, or do you want it to raise some sort of exception and tell you that that primality is not defined for non-integers, for example? Or do you want it to do something more clever? These are the sorts of questions which you need to ask yourself while you're writing the function, and writing tests can help to motivate these sorts of questions as you're specifying what you're doing. So I'm just going to show you a simple example of a script which can carry out one of these tests. So Python comes with a package called unit test, which comes as part of the standard Python installation, which is able to run these tests and includes lots of things which make running these tests more straightforward than trying to write them by hand. But it does mean that you need to include some boilerplate, so some kind of standard things into your script, which will help unit tests to run. So the test which I've written here, this is just a simple Python script, contains this import for unit test, and then it imports our isPrime function from the a file called prime.py where I've saved it. And we set up this class, which is this class is just defined to run the tests on this specific prime module. You can split your tests up different ways, whatever makes sense for the way that you have structured your code normally. And then each of the methods, which is defined within this class, which will define an individual test. One other thing which might be unfamiliar to you if you are new to objects and object-oriented programming in Python is that this class has this relationship to unit_test.testCase, so it is inheriting this class unit_test.testCase, which just means that our prime tests class has access to all of the methods and attributes which unit_test.testCase has defined. So when we look at test number 2, which is our first test that we've written, which is designed to test that 2 is identified as prime, we have this self.assertTrue, and the assertTrue method here is coming from unit_test.testCase. So we say that we want to assert that is_prime of 2 returns true. And an assert in Python, you can use asserts in normal code as well, but though this is a specially constructed assert, just causes the execution of the script to fail if the function which follows it isn't true, or in this case, if the thing which is in brackets is not true. And unit test comes with a number of different asserts, which we'll see later on. Let's do this. So I tried running this test on our code, and we see that we can run I saved the test into test-prime.py as a script, and then you can run it with this slightly changed Python command line. So this Python -m unit test just tells Python to run the unit test program on test-prime.py, and then when unit test runs, it looks through that file for anything which has test in its name and tries to run it. Well, you can see that things didn't exactly go to plan, and that we got told that there was an assertion error and that false is not true. So when I passed 2 to this function, things have not worked as we expected. So this is exactly the kind of thing which you want unit tests for. So they will identify that something which is specified that should happen is not happening, and we can go back to the code and try and work out what went wrong. So you will notice that I have updated the function so that it handles 2 correctly. So what now happens is that it specifically looks out for there are other ways that you could handle this, I guess, as well, but the way that I've solved it is to specifically look to see if the number which is passed to the isPrime function is equal to 2, and to then to just return true to say that 2 is prime. I've also fixed up this line here, which would have caused problems, to make sure that this runs through on a for loop to make sure that each case is tested. So that's good. And when you run the unit tests this time, the single unit test, everything passes, and we just get this. The output is just this full stop to indicate that the test ran successfully and did not error, and we get told that everything is okay. That's good. But this is just one test, testing one case. Lots of other things could go wrong. So if we turn back and think about the various criteria which we specified before, we probably want to turn each of these into their own individual test case. So I've gone through and I've taken the various things, or some of the things which I talked about earlier. So I've kept the test number 2 in here, so the one which tests is 2 prime, but I've added some extra ones to this. So for example, I want to test that 1 is identified as not prime. I've decided that 0 is not prime, so it's okay to return false. So I want to assert that 0 is prime 0 should return false. And the same thing for negative numbers. So if I test -3, and then I want to test an actual prime number, so I'll test that 13 asserts true. Now, when you look through this, you may see, potentially, you may think that there are things missing from this. I'll give you a moment to think about whether or not there is anything missing. And feel free to shout out if you spot something which I should probably have tested. Yep, go ahead. The previous slide. Okay, John, can I just stop you there? We've not run tests on that code yet. No, I'm showing you the test which I will run. Your instincts are correct, though. There are problems. Okay, so the thing which I would argue I should have added really an extra test in here for is that I've tested specific cases of 2 and 1, which I expected to be problematic, and 0 and negative numbers, which I knew would be somehow problematic, and an actual prime number. I haven't tested what it does when I pass it a number which is not a prime number but is not one of these other things. And I think that would also have been a sensible inclusion. And trying to pick a sensible set of tests is to some extent a bit of an art. You generally want to try and identify places where things might go right, well, things might go wrong, but you also want to test the core functionality. And I would argue to some extent leaving out specifically testing a non-prime number is arguably failing to test some of the core functionality. So really adding that in would have been sensible as well. So let's try running, let's see what happens when I run these tests. So this time I get told quite a lot of different things which have gone wrong. So you'll see that because this time I ran 5 tests, I get more output from running unit test of test_prime.py. So when I test that a known prime number is prime, for example, I get an integer division by 0 error. And you can kind of see why this is happening because our range function here is going from 0 all the way up to number. And the first thing which it tries to do is, one of the things which it tries to do And John is right. I have actually fixed. Okay, I'll come back to that in a second. What it will try to do is to divide the number by 0 as part of this test, and it will throw this error. You'll notice, and I think I did this slightly out of sequence when I was putting the slides together, which is my mistake. This is covered in more details in the notes, which I've linked, where this mistake does get discussed. I have left in this num, which is not defined. This would probably have been picked up. This is another one of these mistakes which should have been picked up in static analysis, um, because the analyzer should identify that at no point is num ever defined. But this num should be number. And in the first set of tests, it should have thrown errors to tell you that num is not defined when it tried to run this. And I have skipped this over for the slides, which is my mistake. But yeah, this should be number. But you see that we get these two failures, which we need to go back and address. So we go back to our code, we add some changes to fix it. So the way that we will go about fixing this is changing this range from going from the default which is 0 up to number, change it to go from 2 up to number. Then we can we would run the tests again. And once we'd fixed all of the problems and we'd iterated through all of this, we'd eventually get to the situation where all of our tests run correctly. So we get these 5 dots, one for each test, and we get OK. So this is kind of the process which you need to go through when you write tests, that you write the tests to look for the thing, you run them. If your code passes, then that's good. If it doesn't pass, you go back, you do more development of on the code until everything passes the tests. And you can kind of take this to the kind of logical extreme, as it were, and start by writing your tests before you even write any code. So in effect, the first time that you run your tests, everything will fail because there is no code to work against it. And then you write your code to satisfy all of your tests. And that's a process known as test-driven development. And it's kind of popular, particularly in industry. There's a lot to be said for it. In my experience, trying to actually work like that, particularly on research code, is quite difficult. Normally, it's a good idea. Normally, what I would do is to try and write the very outline of what you're trying to do, write the tests, and then develop from that outline. Other people's mileage might vary, but I find it very difficult to start completely from scratch with tests. But it is very useful if you, as you are adding the non-core functionality to your function, or you want to start defining how it should behave in more complicated scenarios. So you can kind of think in this situation as your tests, defining a specification for your code. And writing tests it's good for making sure that your code continues to run as you go forward in the development process, but it's also a useful I think it's a useful frame of mind to get into, and a useful process to define at the outset what your code should be doing. And it helps with the actual planning of the code and writing the code. Oh, Norman is waving at me. Yeah, I think that's I'd agree completely with that. It's situations where you do know from the outset exactly what the specification of what the code should do is, um, where it's important and where it's really valuable to work that way. So the for example, and it's not necessarily just interacting with libraries, and if it is something like testing for a prime number where you know exactly what the function should be, and you just need to find an implementation for it. As I said, in research, not every problem is going to manifest itself quite like that. So it can be helpful to bring the tests in at an early stage, but not necessarily right at the beginning. Yeah. Um, yeah. So I think that's a good point. So I think testing is valuable on multiple levels. Is kind of the takeaway from this. So once we've got lots of tests and a larger code base built up, uh, we need to start thinking in the same way that earlier on we were talking about keeping code organized and keeping code in modules. We kind of need to start taking the same approach with our tests, and you start building up what's generally called a test suite. Um, and you can do this by keeping the tests for each Python module, for example, in a different file. So that would be my approach would be that when we have, so for our example earlier where we had the all of the kitchen appliances, we would have I would have a separate test file, a test script for each appliance. So I'd have test fridge, test kettle, test toaster, test coffee, whatever, all in different files. Um, and then you can run the tests on each individual part of the code separately. So if you have only made changes to the code for one machine, for example, you could run just the tests for that if that was appropriate. You can also set up unit test to automatically go through and find all of the tests which are in the test suite. So what I've done is move all of my tests and the scripts which do it into a directory inside my project repository called tests, and I've made a separate directory inside that again for my unit tests to separate them from some other tests, which are types of tests which I'll come on to. So all of my tests are in this test/unit directory, and then I can just run Python -m unit test with this discover keyword. So this allows unit test to go through the entire directory of test/unit, looking for any file which starts with the word test, and then looks through it for any class which starts with the word test, and then any method which starts with the word test. The unit test documentation talks a bit more about ways of laying these things out, which I'm not going to go into right now. Yeah, the suggestion here is that you keep unit tests inside a directory called unit inside a directory called tests. It's not completely normal to always see this division in Python projects. Quite frequently, the tests are all just sitting inside the tests directory. Um, it depends really how many other kinds of tests you have set up, whether or not this makes sense. You have flexibility to choose to or whether to or not to do this. So, in addition to unit tests, as I alluded to earlier, unit tests that we have end-to-end tests or regression or integration tests. So unit tests are very good at checking that individual blocks of code run as you anticipate and as you expect, but very few programs involve only running one function. And normally you'll be running lots of functions in sequence, and you'll want to check that everything works together in that sequence or in some subset of that total sequence. And that's where the concept of integration tests comes in. So these follow the same basic principles as unit tests, and you can use the unit test package to run them. And you just need to write tests which have multiple steps inside the definition of the test. But it's often a good idea to keep these separate from the actual unit tests because they might take a long time to run. So, uh, for example, you might want to set things up so that you are running your unit tests every time you are preparing a commit going into a repository. But it may be that if you've got some particularly complicated code, you only want to run integration tests once a night, for example, and you want to set your the system for running tests up to do that nightly. So, for example, I work in gravitational waves where we do a lot of Bayesian inference on things, and running end to end running an integration test on some of our programs could take several minutes or even hours in some cases. So it's clearly not something which you want to run every time a commit is made to the repository. So we keep our integration tests aside, and they're run through what they used to be run through a cron job. We now have integration systems which run more frequently, which run through GitHub and GitLab to do this, but they're run on they're run once a day. So when producing nightly builds rather than every time a commit is pushed to the repository, for example. So it just can be helpful to keep these sorts of things separate. Then the final category of tests, which I'm going to talk about, are regression tests, which are kind of similar to the concept of integration tests. But with research code, and particularly with scientific code, you will frequently have the code reviewed at some point. So there will be a version which was used to produce a paper or produce results which were published, and which you will want to have sort of pinned as being as working results and the correct results which the code, the pipeline, whatever you're writing, should produce. And it can be valuable to ensure that the output from the code continues to be the same for a given set, say, of data or parameters. And regression tests, again, follow the same basic principles of all of the other types of tests. These are ones where we have some reference output which we want to compare to the output of the program at any given point in time. So again, regression tests can take a long time to run, which is why it's a good idea to potentially keep them separate, particularly from things like unit tests. And it might be that you run regression tests even less frequently when you are preparing, for example, a release of your software. And we'll talk about releases of software later as well. But it may be that you only run these when a new version of the software is being produced to make sure that it is producing the same results as older versions of the software. So again, looking at the sort of thing which I do, the types of regression tests you might do might take several days and might require extensive computing resources. So these really are things which you don't want to do very frequently, but their existence can be useful to ensure that there is continuity in the entire code base in what it's producing. And yeah, so these tests might be a bit more complicated in my experience as well, because you aren't necessarily checking the results are exactly the same. Frequently you're testing the results are the same to within some tolerance. And if you're working on a data analysis task, for example, you might need to add some extra flexibility into your tests to allow for stochastic elements, for example, or else do extra work to ensure that things like random seeds are set correctly. So Yeah, all three types of tests are valuable. Um, Unit tests are the one which I think you should try and have with almost any code that you write. Things like regression tests really are for the big for bigger pieces of software where which are used for results which are going into papers. But all three types can be useful in different situations. So the second topic in this session then is documentation and how you and strategies to make sure that both you can run your code at some point in the future and understand what it's meant to be doing, and that anybody that you're working with or who is going to use your code at some point in the future can understand what's going on and can use it. So it's always a good idea to. Oh, Norman is waving at me. Yeah, so there are strategies which you can take which I don't really have time to talk about at all, except for mentioning. So you can set up things called hooks into version control systems like Git to automatically run tests before the commit gets made, which can be useful if you are as disorganized as I am and would forget to run your tests. So if your tests fail, Git will just refuse to produce a commit object and will tell you to go and fix your tests before that can happen. That's a that's a mixed that's a mixed blessing and kind of a double-edged sword because it can also stop you producing a commit at 4:59 in the afternoon, and and if you do not have the energy to go fix your tests, you may end up causing yourself more problems. Norman is waving a finger at me. Oh yeah, that's yeah. So when go ahead. Yeah, yeah. So once we've written our tests and we've got our commits committed to our repository, it's a good idea to start thinking about documenting your code. And this is another thing which should really be part of your coding process right from the beginning. It really is a good idea to make sure that you've documented your code, because even if you are the only person you expect to ever be running this code, at some point in the future, you will forget how it works. And I can assure you from having failed to document various pieces of code which went into my thesis, the best time to not discover, sorry, the worst time to discover that you have not documented your code well is in the last couple of weeks, when you actually need the results and you are not in the mood for messing around. So do it now and do it when you start writing your code and try your best to keep up with the documentation as you go through. Future you will thank you. Um, the most fundamental unit of documentation in most software projects is what's called the README file. So this is just a file which sits in the root of your repository, and it's just a text file normally. Traditionally, it is just a plain .txt file with no particular formatting. It sits in the root of your project directory, um, uh, and is committed into the root of your repository, so that when you go onto GitHub, for example, it's on the first page of what you see. And code sharing services at GitHub will automatically pick up your README file and normally display them alongside the repository for you. So it is also a useful thing to advertise what the repository is for in those situations. Services like GitHub and GitLab will often support some markup, so some formatting within the file, so that it can understand things like headings. So two popular ones are Markdown is reasonably universally popular between lots of different programming languages, and restructured text, which is I think more common in the Python ecosystem because it was developed for Python documentation. But restructured text is slightly more flexible, has slightly more features, and is slightly more flexible than Markdown. The examples in the rest of this session will use restructured text, but you might find Markdown easier to work with. And I have strong opinions about which one I like, but I don't have strong opinions about which one is the correct one or the best one. Use whichever one you will write, I think is the sensible thing to do here. So just having a look at an example README file for what should go into it. So the very first thing which should be in your README file is the name of the project or the name of your software. And you should probably choose something slightly more descriptive than just example project. But right now I'm looking at my example project, so it kind of makes sense. And it should have a short description, so 1 or 2, maybe 3 sentences, but something nice and concise, which just describes exactly what the software is designed to do, and which somebody can hopefully work out the gist of what the project is for in a fairly quick glance. It's a good idea to have a very concise guide on how to run the code. So if my code, for example, provides the command line program foo, I can just run it by running foo on the command line, and that is a nice concise guide to running the code. And some instructions about installing the code. So if this was Python, for example, I could run something like pip install example, or frequently you'll get some additional instructions about how to actually compile and install the code. So instructions about compiling it from the source code itself using make. So for example, telling you to run /configure make install, which is a very frequent pattern in Linux and Unix software projects. Then just a brief list of the main features of your software should go next. If you are looking, and generally if you are putting your code somewhere that's available on somewhere like GitHub, you're probably at least open to the idea of other people contributing to your code. So it's a good idea to put some information about how you would like them to do that. I guess if you don't want them to contribute, you could explicitly say, stay away from my code. But it's probably not the best way to get help or to get people to use your code. And then finally, and this one is kind of important, it is frequently missing from especially scientific codes and is problematic on many levels, is information about the licensing. So information about how or whether other people should be allowed to use your code, either to run it or to modify it. Now, I'll come back to talking about licensing when we're talking about packaging your code, but information, at least a couple of lines about reusing and licensing of the code should go into your makefile as well. So, for example, if I had chosen something called the MIT license, I should specifically say that it's licensed under the MIT license, but that it's copyright 2021, Daniel Williams, or whatever. So this is the very skeleton of what should go into a README file. There are other things which might go into a README file as well. You can basically include whatever you want, but it's generally a good idea to keep it reasonably clean and make sure that things like this are in it. Certainly, if you expect anybody else to come along and use your code, having these things would be helpful for them. And there's a decent chance by now you have encountered README files yourself, and you probably know what makes a good README file just by instinct by now from having seen examples of both good ones and bad ones. And if you have been sufficiently unfortunate, you may have come across repositories which have no README file in them at all, um, which is especially unfortunate, but also quite common. So really, do try and have something like this. And as I say, because GitHub will render your README file for you, it is also very obvious when you encounter a repository which doesn't have one, and it just looks bad. Then the next thing, the next kind of level of documentation which I'd advise that you try and include with your code is what we call code level documentation. So as your project's getting larger, the amount of code which you need to remember the ins and outs of and how to run will start to increase. And it's going to start to become more and more time consuming to pick through your own code to try and work out how it works if there aren't notes to explain it. Now, all programming languages will have a syntax for comment. So in Python, anything which is on a line following a hash character becomes a comment. But it's also got the special string called a doc string, which I talked about earlier, which is this the first line in a function or a class. When it's provided as a string, is turned into a doc string, and Python allows multi-line strings with the triple quote syntax. So normally you will see these doc strings surrounded by triple quotes. Sorry, triple quote characters, not triple. Yeah. So as an example, you can see exactly this in this example, and once again, strong example that I code too much whilst hungry. Also, for a code too much whilst hungry and about specific things. I think I was writing this example up presumably around Christmas. So I've got a Python function here which takes pigs and blankets and it wraps pigs in blankets. So our function starts out with this set of text, this string rather, this multi-line string starts with the three double quotes. Very brief 1 to 2 sentence description of what the function is meant to do. So it wraps pigs in blankets. Then this section which lists the parameters of the function, so the things the inputs which it takes. So I say that it takes a pig, which is a string, and that's a digital pig object. A blanket also as a string. So the name of the parameter, its data type, its expected data type, and then a description. In Python, it's particularly useful to describe the data type this way because Python is generally a weakly typed language, so you can pass things which are not of the expected data type to a Python function, and it may not realize that this is happening until well into the execution of the function. So it can be useful to include this in the documentation. And then this docstring also contains a very brief description of what the function actually produces. So it produces wrapped pigs, which are coded into robed digital pigs. So these are kind of the things which should be present in the docstring as a minimum for your function. So the very brief description, the parameters, and a description of the returns. There are lots of different standards by which you can write these doc strings. You should choose one and use the same thing throughout all of the code in a given project. This one, the one which I've chosen, the one which I strongly favor is this NumPy doc one, which was developed for the documentation of NumPy, which Python users are probably familiar with already. Is a major numerical computing module for Python, and it's just I think it combines readability with flexibility better than any of the other ones, in my opinion. This website, numpydoc.readthedocs.io, talks about lots of the other things which can go into a doc string and how you should format it, and it provides a set of rules which are really quite useful to follow and useful to go through to make sure that you've documented your function well. And then there are tools which I'm only going to mention the existence of. We don't really have time to talk about them in any detail, which can go through your code, read these, and automatically compile human readable documentation of these. So they can make web pages and PDF files, for example, which contain all of this documentation. So if you've ever looked at the documentation for a Python library or even for the Python language itself, you'll have encountered this automatically generated documentation, which is produced using a program called Sphinx, which I think I talk about on the next slide, hopefully. Yeah, I'm going to point you to where you can find out about this. So you'll normally be including extra information as well as this code level documentation. And that's normally going to be too lengthy just to include in the README file. So if you've got things like tutorials or notes about how the code works, or more detailed usage guides for your code, you will want to write those up and include those with your code in the repository. The kind of a de facto standard, and certainly what I would do, is that you keep your documentation within a subdirectory of your repository called docs, which will contain all of the extra files which make up your documentation, and which you can then use an automated documentation builder with to take all of these things and compile them into web pages or whatever exact form you want. So in the Python ecosystem, the kind of de facto standard one of these is called Sphinx. I've got some moderately extensive documentation at this link about how to actually use Sphinx and to create web pages which use it. The notes themselves were written using Sphinx, so you can kind of see the. Let me see if I can. I've got a couple of minutes. I'll bring this up so you can see that it can produce web pages which look like this. And to do this, you just pass some extra information in a configuration file to tell Python to tell Sphinx how to compile your project documentation. So that is us almost at the 50 minutes. So I'm going to pause and ask if there are any questions or comments. Okay, well, I'm going through this very slightly faster than I'd expected, but I'm more or less on schedule. So I'm going to suggest that we break until 4 o'clock and then come back for the last 50-ish minutes at 4 o'clock, where I will talk about what you need to do to prepare your code for distribution and publication. All right, see you shortly. All right, let's get started again on the final section for this afternoon. So hopefully this shouldn't take too long, and we might get finished just a little bit early. But the final section, and it is possibly covers the what's going to be one of the more important aspects of writing your code for you, which is seeing it through to publication. And increasingly, journal papers are expecting that you publish your code, that you make your code available alongside the results which are actually in papers. So this is becoming an increasingly important aspect of the whole process for everyone, not just for people who are writing things like code libraries or codes which you expect to be used widely afterwards and widely distributed. The first thing which I want to talk about is to come back to a topic which I mentioned earlier, which is licensing. And this is kind of one of the more dull aspects of what you want to decide, but it's what you need to do to ensure that other people are legally allowed to download and use your code, and you need to explicitly permit that under copyright law. And of course, this is not legal advice, but this is the practice which is normally taken is to specifically license your code and include details of that license with your code. And normally this is done by choosing some pre-existing software license, and that license will affect exactly what people are allowed to do with your code and to what extent it can be modified. So there are two broad families of open source licenses which allow people to look at and modify the source of your code, so to continue development using your code. So those are licenses which fall into the category of copyleft, and licenses which are described as permissive. So copyleft licenses and GPL licenses, which are which allow people to these allow people to run your code, look at your code, and modify your code, but they are somewhat restricted in how much they're allowed to redistribute your code. So for example, if you provide your code and somebody uses it, then wants to use it as a component in some other code base, they can do that, but they have to distribute your code under the same license, with both the GNU General Public License, the GPL, and with the Creative Commons Share-alike license, which are the two most common examples of this kind of license. So in practical terms, what that means is that your code can't be incorporated into paid-for software without your further permission. And that might be a positive thing, or it might not be a positive thing, depending partly on your own outlook on things and partly on what requirements are on you of your either employer or your funder. Permissive licenses, which include the MIT license, the BSD license, and the Internet Software Consortium, I think is what ISC stands for, licenses, allow people to do a lot more with your code. So they don't include this prohibition against including your code in differently licensed projects, and that means that your code can be reused in paid-for projects and normally freely. I would generally advise that if you are not sure about what kind of license you should use, you should check with somebody like your supervisor or somebody higher up in your research group who might know this, because there may be specific requirements put on you by your funding agency or by your university, for example. But ordinarily, I use the MIT license for projects or the ISC license, which are very similar. But as I say, I think it's generally a good idea to check what the requirements are, what specific requirements are on you and you may have different opinions about the goodness or the badness of allowing people to use your code completely freely. And this is not, I'm not here to talk philosophy, just which licenses exist. So the way that what you normally do with one of these licenses is that once you've decided on one, you get the text of the license and you include it in the root of your project directory alongside the README file as a file called license. To make this whole process easier and finding the text of individual licenses easier, services like GitHub normally allow you to include a license file automatically when you're creating an empty repository. And if you are creating an empty repository on GitHub for the first time, and so you're not pushing a repository which is already on your machine, I'd suggest that you take advantage of this. It cuts one step out and makes life slightly easier. Yeah, so I think that's what I've got to talk about with licensing. But once you've got a license and you've got your code and you're getting ready to package and distribute your code, the next thing which you probably want to start thinking about is how you will keep track of different versions of your code and how you differentiate between those different versions and what features and various backwards compatibility should exist between those versions. There are different ways of doing this, and you're probably familiar with some of them or have seen some of them. So some major software projects like Firefox and Chrome increment their version number very frequently and end up with very large version numbers. That's reasonably uncommon, and I'm not so keen on that approach. Then there are other approaches like what Ubuntu takes, which is to have a regular release schedule where each release is formed from the year and the month that it's released, like 21.04, which will be the next version of Ubuntu, for example, because it will be released in 2021 in April. Those are two approaches. Neither of those is the approach I'm going to suggest. The scheme which I'm going to suggest here is semantic versioning. As I say, it's not the only game in town, but it's probably the most straightforward choice if you are starting out from a new project. So a semantic version number, you will almost certainly have seen one of these before, or something which looks very similar. It takes this form of major.minor.patch. Now, what does that mean? Well, these are three hierarchical parts of the version number, which each describe a slightly different aspect of the development of the code. So the bit out front, the first section, is the major. Python users in the last couple of years, for example, you might have been aware of this as being as the differences between Python 2 and Python 3 being exactly an example of this, of changes to the entire code which break old code. And so where things behave differently and where code which is designed to run in Python 2 will not necessarily run in Python 3. So when a major version changes, it means that code which relies on that should not expect to be able to run necessarily as the major version changes without changes to that code itself. Then the minor version is for it gets incremented when new features get added to a code base. But those features don't break backwards compatibility. So they are additions to the code, but they don't change how the code works. So for example, if new functions had been added, but the names of those functions had not been changed. If the names of the functions had been changed, we'd need to increment the major version number because code which is looking for a function which has had its name changed would not necessarily be able to find that would not be able to find that renamed function. And the third part of the version number is this patch version. So that gets incremented whenever there are bug fixes, so things which do not implement new features in the code and new functionality to the code, but continue to be backwards compatible and fix the behavior of the code to fix things like bugs, for example. So these do not add new features. So so whenever a one of the numbers changes, all of the numbers which are below it in the hierarchy are reset to 0. So, excuse me. So this is a valid sequence of version numbers. So 1.0.34 to 1.035 is fine, and then if a minor version gets released, it would become the first minor version after this would become 1.1.0, so the patch number gets reset. And then if the next release is a major version, then it would become 2.0.0. And the other thing worth noting about how this all works is that the major version 0, so versions 0.1, 0.2, and so on, are special, and they do not generally require that your minor versions remain backwards compatible. So version 0 is a special pre-release state of your code where everything is kind of the Wild West until everything settles down. So if you come across, so this is kind of a useful thing to know about anyway. If you come across code which you are using as part of your project, which is a version, 0.3.1, you should be cautious about using it. I'm not saying that it's necessarily bad, but you should be aware that as that code develops, it may develop in ways which new versions may break your code, because there's generally no guarantee with projects which use this numbering scheme there's generally no guarantee that backwards compatibility will be maintained. However, as soon as you have decided that your code should be backwards compatible, and basically as soon as you are pushing towards a proper release for your code, as opposed to pre-releases like this, at version 1.0.0, people should be expecting to have backwards compatibility between minor and patch versions. So the v1.0.0 is generally a milestone in the development of whatever your code is. And for example, if you were using code or publishing code alongside a paper, it's quite probably a good idea to aim to have version 1.0.0 happening around about then, since there's a decent chance if you are expecting people to use your code and to use results from your code that they should be able to use it plus any bug fixes without having to go and rewrite large sections of code every time you make a new modification without pushing to version 2 or version 3. So kind of in the theme of tying things together from the last couple of weeks, Git allows us a particularly useful tool for keeping track of versions of code. So each commit which you make in Git is unlikely to represent a new version, but a series of commits will eventually build up to something which becomes a version, and you'll want to tell Git whereabouts in the history of the repository a specific version is defined. So once you have a commit which you intend to turn into a released version, you can use something called a Git tag. So this is just an extra piece of information which is added to a commit in your Git history to tell it to give it a name, basically. So, for example, if I'm preparing the release from a given commit for version 1.0.19, I can run git tag -a for annotate v1.0.19, and I can also include a message if I want to explain what that version is with -m, the same as you do for a commit. And this adds a tag to the repository, and when those tags are pushed back to GitHub, for example, GitHub uses those tags to identify releases on the repository, and then when you see on GitHub on the sidebar, it'll say that a given project has 19 releases. It does that by looking at the tags, and you can then annotate on GitHub the releases additionally as well. Okay, so the next section is going to swing back to being a bit more Python specific again. This really is quite Python specific. Um, it's in here partly to tie up some loose ends from earlier, but for the most part, the concepts which are in this are going to be somewhat transferable to other languages and to their ecosystems. For some of you, that may be less true. So things like MATLAB, which handle packaging really quite differently, uh, yeah, you may get very slightly less out of this, and I apologize, but hopefully this will point you in the right direction if you are using other languages. Or I may be wrong about MATLAB. I'm not. There may be better packaging tools for MATLAB than I know of. Lots of the things which are done in this section for Python, Python does in a specific way, which you would generally do with make files for projects which are built in things like C and C++. So Python has its own. Uh, Python has to some extent reinvented the wheel of make files as well, and which is why make files are relatively uncommon in Python repositories. So the whole process in Python of producing a package uh, really requires us to think back to how we were producing modules earlier with all of our kitchen appliances code. So you'll remember that I specifically said that we needed to include our code in a directory alongside our coffee time script so that Python could find it. Now you could move that file and then change lots of environment variables in on your machine to allow Python to find it, so adding it to what's called the Python path. But um, that's kind of cumbersome, and equally having to copy the directory to be alongside your scripts all the time is going to be ungainly and cumbersome and potentially error prone. Um, but instead, Python, not Git, Python, sorry, Python provides a toolkit for installing your code to a place where it can be found by scripts running anywhere on your machine. Um, And to do this, we need an additional script in the repository to do this. And by convention, that script is normally called setup.py. So yeah, so yeah, just to come back to, and I fixed this thing from breakfast to kitchen, to have a look at the sort of structure which we need to have in our repository. We have all of our code inside this kitchen directory, and then all of the various modules within that exist here in the init.py file. And then we have our setup file, which is at the same level as kitchen. And we'd also have things like the README and the license file sitting here as well. So this setup.py file is a script which contains some specific boilerplate, so some specific a specific function which allows Python to identify everything which is, oh, this has got a mistake in it. I did this quite late last night, but I'll talk about what the mistake is, and it should be correct in the actual note. But uh, the setup function just tells Python how to identify what the components of the package are, what they should be called, and some extra information about it. So the first thing which we need to do to make this work is to import this setup function from setup tools. Setup tools is a part of the standard Python library, so it comes with a standard Python installation. And then we give it some keyword arguments to describe that package. So this is kind of a minimal subset of what you need. I copied this setup file from another project, which is where the mistake came in, and I'll point that out when we come to it. So you tell it the name of the project, so kitchen. You give it a description, which can just be one line to describe what this project does. Tell it the author and your email address. List the packages, so this should in fact say kitchen inside it. then tell it whereabouts in your repository kitchen lives. So this should say kitchen:kitchen. I stole it from a repository called Asimov, where the package is called Asimov and lives in a directory called Asimov, which is what's going on here. Tell it the what license the code is released under, and then this thing about zip safe, which you can generally say true. You should check the documentation for setup tools about this, though, if you have anything basically if you have anything other than Python files which need to be in your package, you need to concern yourself about this. But that's kind of beyond the scope of this course. So yeah, this tells Python everything which it needs to know to install a package on your system, but it also gives it the very basics of what it needs to know for the distribution step, which I'll talk about in a moment. So that's why we've got some of this additional metadata, which you might not immediately think is necessary just for installing the code. So to install your package, once it's set up with this setup.py file, you can run python setup.py install. This is kind of old-fashioned and slightly disapproved of these days, and it's generally preferred that you run pip install dot. So pip is the package manager for Python, and it allows it's a system which allows Python to go onto the internet, find packages, and install them onto your system, as well as installing ones which are locally. So pip install dot just tells it to install the contents of the local directory. So if you run this in the root of your repository, it will install your, in this case, kitchen kitchen library onto Python, where any code will be able to run import kitchen and then find that piece of code. Now I've left a note here to say that you may need sudo rights to run either this pip install or the python setup.py. That's because by default Python will attempt to install the code onto your computer in a way which requires sudo access, so into a part where the whole system can find it. Pip will normally run without sudo, and it will install it somewhere that only your user account can find it, but that doesn't work on older versions of pip either. In both cases, it's probably not the best idea to install directly onto the system like this. And we don't really have time to, well, we might just about have time to circle back to this, but I think we probably won't have time to talk about alternatives to installing directly onto the system. But instead, Python and other languages have systems for separating your development code from everything else which is going on in your system. And in Python, these are called virtual environments. There are some notes on these, which are linked in the slides and which are also included in the link which is on the middle page, which talks about how these work. And virtual environments are generally a good idea for a couple of reasons. One, if you are working with code which has specific dependencies on, if your code requires a specific version of some library, you can define that within that environment without installing it onto the entire system. And installing new versions of libraries onto your system is risky, can be risky, because your system may itself depend on specific versions of those libraries. And these virtual environments just are designed to make your life easier in many different ways, and the notes discuss what some of those are. But the takeaway basically is go learn how to use these virtual environments, and they will just make your life. They will make your life easier in many ways. If there's a bit of time at the end, I might circle back to them, but I don't want to fixate on them right now either. So once we've got our package built up like this and ready to install, Python has also set things up enough that this is basically ready to distribute as well. And as I alluded to earlier, one of the particularly powerful features of Python is its package management system, pip. So I can just run on the command line pip install numpy, and pip will go and search through PyPy, which is the Python package index, and it will go find the latest version of NumPy for me, download it, and install it onto my system. So to distribute our code, the easiest thing for other people is to make it available through pip. So if we wanted to make our kitchen package available via pip, there are some additional steps to do this. And there's a program which basically automates the vast majority of this for us, called Twine, which really, so previously, until quite recently, there were several extra steps in this process, but Twine, which is the official client for installing these things, makes it a lot easier. So you can install Twine onto your system first by running pip install Twine, and then we need to produce a binary distribution of the code. So binary distributions in Python are handled by something called a wheel, but we can also produce a source distribution, so packaging up all of the text files and the program files which constitute the source. So these things are bdist wheels and sdists. So the setup.py script is able to produce both of these. If we run python setup.py bdist wheel and sdist, it will, provided it's able to run, it will output both of these into a directory called dist inside your repository. So you do not need to commit these things to your repository because they're able to be built from the things which are already in the repository. And then once you've signed up for a username and password for an account on pypi.org, you can just run twine upload dist/star. It'll ask you for your username and your password. It will upload all of the necessary files to PyPy, and people will be able to run pip install kitchen to download and install kitchen, in this case, on their own system. So this is in fact my last slide. So I'm going to break briefly to ask if there are any questions. If there are no questions right now, I'm going to take a couple of minutes just to introduce this concept of virtual environments, just in the notes. So I'm not going to set one of these up in front of you, but I will. I just want to make you aware of what they are and of their existence, because I do think they're kind of important, and I shouldn't have skipped them out of the slides. So there are two major approaches to that to virtual environments in Python at the moment. One is built into Python itself, which are Python virtual environments, and the other one are Conda environments, which are provided by a packaging ecosystem called Conda, made by people who produce a specific distribution of Python. I'm not going to talk, my notes don't really cover Conda environments in much detail. They are very useful if you need to run non-Python code alongside your Python code. So in LIGO, for example, we have a major suite of C codes which are accessible through Python, but which need to be built through a more complicated process than what pip can do. So Conda allows for that. So there are situations where you might want to be able to use Conda environments. I'm only going to make you aware of their existence rather than talking about them in any detail. For the Python virtual environments which are built into Python, these are really quite easy to set up. So if you have your code in a repository, you can run python 3 -m venv, and then just, for example, write env here if you're running it in the root of your repository, which will create a directory, um, uh, which can store all of the Python libraries which you're going to use in it. Um, if you are going to do this like that in your repository, you will want to make sure that that does not get committed to your repository. And I have some notes about how to specifically avoid that happening here. The other approach, which is the one which I would normally use, is to have a directory on your machine which you keep your virtual environments in which case you can run something like Python 3 minus mvn. I keep all of mine in a directory called .virtualenv, so it's a hidden directory in my home directory, and just this new environment. Then when you come to run your code and you want to run tests and so on, you can activate your virtual environment by running a command like source and then taking the path to the environment, so slash, home slash virtualenv slash new environment slash bin slash activate. So this just runs a little bash script which resets some variables on your machine, so that Python goes looking for libraries inside the virtual environment rather than on your system. And then once you have your virtual environment activated, your prompt will change, so that it'll tell you that you're in an environment called env, for example. And then inside this environment, you can run things like pip install numpy. And then they'll be installed just inside that environment, so that your environment is isolated from the system as a whole. And when you're done and you want to go back to being able to run in your system as a whole, you can just run deactivate, and it will undo all of this, and all of the system Python will operate as normal. And there are various things which you can kind of build on and elaborate on this with. So if you need different versions of Python, you can use a tool called pyenv, which can create virtual environments which have got different versions of Python. So if you want to test whether your code will continue to work as you expect in Python, in the latest and greatest version of Python, so which was Python 3.8 when I wrote these notes, I guess would be Python 3.9 or 3.10. Now you can do that this way as well. So I'm not gonna labor this point too much. Just go check the notes about how you do these, how you use these. Strongly recommend that you do use them, because they will help you keep track of dependencies and to not break things on your system. So they are generally very much a good idea. I'm going to finish up there, and ask again if there are any questions or comments, or either about this or about any aspect, I guess, of the course before we finish up. Yep. Um, Sort of, yes and no. I mean, so GitHub would be where your entire repository is, which, so for including all of the development of the code, you would normally only push releases to pip. So, when you have a specific version, it goes to pip. Um, so how I have this set up, and I have not written notes about this yet. It is on the to-do list for my notes. Is that you can set GitHub up so that it will detect that you have produced a new release when you push a tag. It will then run all of the distribution steps, and it will push that release to PyPy so that people can get it more easily. So the idea behind this, I guess, being that if people just want to use your code but aren't interested in developing it or looking at how it works, you can just run pip install kitchen, in the same way that if you are using NumPy, for example, chances are that you don't particularly want to go look at the source of NumPy. You just want to be able to take advantage of its functionality. So you can run pip install NumPy. But it also exists on GitHub, so that if you did want to go look at the code, you can go to the NumPy project on GitHub and download the entire repository. But installing directly from the repository is more complicated. So normally, yeah, you would generally have both. Yeah, yeah, and I can think of a very good example of this, which some of you might have encountered um, recently, which is TensorFlow, which is a machine learning framework for Python, which is reasonably straightforward to install through pip, but is a complete nightmare to build from source because of how many steps are required to deal with the actual production of the distribution. And because it's obviously a much more complicated build process than what I described in my slides, but there are more complicated build processes which can produce one of these wheels, which can then be pushed to PyPy so that you just install the wheel rather than having to run the entire build process. Any other questions, comments, confusions? I know for some of you who are PhD students in my own group, you must be quite close to this stage, and so it will come certainly for IGR people. This will almost certainly become a part of your life, I'm afraid. Yeah. Okay. Well, I mean, if nobody else has any big pressing questions, the recording of this part of the lecture, because I appreciate that I went through everything kind of at breakneck speed, and there's just no other way. Well, I guess I could have taken an extra 20 minutes, as it turned out, but there's no way of doing this in any great detail in the time that we have. So the recording will be on YouTube. I will put a link to it on the middle page once we're done. Uh, I'll put the link to that on YouTube once we're done. sorry, I'll put the link on Moodle to the YouTube video once we're done, which hopefully everybody should be able to get hold of. Um, and there are the notes linked on Moodle. But yeah, I don't know if we've got anything else to say to finish up, Norman.